Good morning, everyone. Welcome to the session on gravitational wave source modeling. We have a set of 5 talks, followed by a panel discussion later. The first talk is an overview talk by Professor Harald Pfeiffer from Max Planck Institute, AEI Potsdam. And then we'll have a set of 4 talks afterwards. Harald?
Yeah, it's a pleasure being here. Thank you for the invitation. Unfortunately, I couldn't be here yesterday, so I apologize in advance if I might repeat something already said yesterday. Can everybody hear me? Good. Source modeling, gravitational waveform models are at, well, yesterday you've heard a lot about all the successes of the gravitational wave so far. And the point of today's session is knowledge of the waveform, so-called waveform models. And you need to know the waveforms of the anticipated events for a wide variety of different reasons. First, events are detected with matched filtering. Second, parameter estimation works by comparing the observed data to the expected waveform models, waveforms for all different masses and other parameters. So the colored region in these types of plot actually is constructed by calculating waveforms everywhere and then checking whether the waveforms agree with the data. Testing GR, I believe, is obvious. How can you test a theory if you're not able to evaluate the predictions? And another reason for doing waveforms is to do validations, where, for instance, one can inject one waveform into a LIGO noise and test the entire recovery pipelines, making sure you get back what you have put in. There are 3 different methods for modeling compact binary objects, primarily depending on the distance of the bodies. In the early in-spiral phase, when the frequencies are low and the velocities are low and the system is nearly Newtonian, there's post-Newtonian and post-Minkowskian expansions that can be used. For black hole ring down, again, analytic results from black hole perturbation theory. And in the middle is the realm of numerical relativity, solving Einstein's equations without any approximations on supercomputers in the full nonlinear form. Besides stage of the in-spiral, the second most important parameter is the mass ratio from comparable masses where numerical relativity works well to extreme mass ratios down here where one can do small mass ratio perturbation theory, usually called gravitational self-force. So all these different methods exist and they are all useful, but none of them spans the entire parameter space. So if you want the complete behavior of your binary from early on to late, you always need to combine different methods together. And of course, these 2 parameters here, mass ratio and distance, isn't everything. There's a large number of additional parameters floating around. The mass ratio, why do I list masses again? Well, the spins of the objects, whether you have orbital eccentricity. For neutron stars, you need to worry about the equation of state and tidal effects and disruption. There may be astrophysical environments around your binary, like accretion disks, or affecting the propagation of the gravitational waves like lensing. And there may also be, you may also be interested in studying other alternative theories of gravity where you want to put in beyond GR effects as well. So when combining different models together, we have a long list of things away from, sure.
About the last slide. I noticed at the very bottom here. I noticed at the very bottom here, you know, if you want to do things completely analytically, well, you can use post-Newtonian, post-Minkowskian for the small mass ratio, and then you could go up. But I noticed that you drew your, so it doesn't quite overlap black hole perturbation theory, as if you can't actually do analytically the complete small mass ratio. Is that right? That lack of overlap between black hole perturbation theory, is that deliberate?
So this lack.
Yeah, exactly. That's what I was asking about. Is that just, you didn't draw it so carefully?
I think it's a combination of drawing and the fact that the small mass ratio approximations can't do the transition to plunge just yet. But all the boundaries in this diagram are very fuzzy. They aren't precise thin lines. And whether you have overlap somewhere depends primarily on the required accuracy that you want to achieve. And the higher accuracy you want, the smaller the region of validity becomes, and also of the parameters of the systems. So to do waveform models that do everything, we have a long list of things they should achieve. So we want to have typically full in-spiral merger ring down waveforms. They need to be continuous in parameters, not like numerical relativity simulations that happen at discrete points in, say, spin mass space. You want something that you can evaluate for any floating point number. They have to be fast enough for parameter estimation and all the cool applications talked about yesterday. They have to be accurate enough, and accuracy will play a major role towards the end of my talk. And accuracy also includes things you might not think so much about, like both Bondi-Metzner-Sachs frames, spin directions, how to define eccentricity. They need to include ever more physical effects, spin precession, eccentricity, both. For neutron stars, black holes, EOS, tides, disruption. We want, of course, higher order gravitational wave modes, not only the 2-2 modes, but ultimately also things like gravitational wave memory, or perhaps even the tails of the gravitational wave ring downs. Black hole kicks, orbital resonances, those are way off in the future in terms of relevance and applicability. Well, orbital resonances are really important for LISA. And already, as I pointed out, environmental effects and beyond GR effects. So there's a lot of things that need to go into waveform models. And we want to have all these features for ever larger portion of parameter space. The LIGO gravitational wave events are quite kind in the sense that most of them are in fairly easy parts of parameter space, mass ratios close to unity, spins not too large, eccentricity small, but we are not guaranteed that the same is true in the future, and we want to be able to analyze the really cool outlier events in the future as well. Yeah, so how do you actually go about combining things? We have very broadly said on the left-hand side the analytic results for the in-spiral, and R to bridge the in-spiral, late in-spiral into the merger regime and connect to the quasi-normal modes of the black hole ring down at the end. And we have separate talks for the analytic results by David and Ricardo, and Kenta is also expanding a lot about numerical relativity, in addition to what I'm saying here, but I think Kenta is also putting in all the neutron star and meta topics that I'm skipping here. There's basically 3 big families of waveform models that are being used in today. Effective one-body methods start out with a resummation of post-Newtonian data into a one-body form, and they center on having a Hamiltonian and then using Hamiltonian dynamics to evolve it. Phenomenological models start basically with power series directly in the Fourier domain for the gravitational wave modes. In the in-spiral phase, they typically use post-Newtonian Ansätze. In the middle phase, they use numerical relativity inspired Ansätze, essentially looking at many NR simulations, discerning what types of shapes and functional forms appear there, and then writing those down. And the ring down are quasi-normal modes. And in both cases, there's 3 parameters built into these models. For instance, in effective one body, you can add higher order post-Newtonian terms into the Hamiltonian, or you can put modifications into the waveform modes. For the phenom models, there's, because it's basically power series, there's a lot of free coefficients in the power series. And all these free coefficients are then calibrated or fitted to agree with numerical relativity results in the late in-spiral regime where numerical relativity simulations are available. The third approach are numerical relativity surrogate models, which are fancy techniques to take a large set of NR simulations, like 1,000 or 2,000 displayed here in the mass ratio spin space, and directly construct interpolation formulas and interpolation functions that give you the results directly. All these models have been developed in such detail and depth that I can't really do them justice at all. So what I'm showing up here is the tables from the LISA waveform white paper about EOB model development. The two major families are the SEOB and R waveforms and the EOB ReSum S waveforms. And typically over many years, many versions, generations of these models are developed that become more and more accurate, that have more and more post-Newtonian information, that are fitted to more and more accurate numerical relativity simulations as well as you go down. Also, the number of modes around goes up from just the 2-2 mode to ever more. And they also include spins and precession. And now the latest new addition are eccentricity already coming in as well. For the phenom models, the storyline is quite similar, a long sequence of steps. Phenom A was developed back in the early 2000s, I believe, by Ajith. And a lot of number of people have worked on this over many, many years, improving accuracy, physics content, and most recently also putting in eccentricity. For the surrogates, I don't have such a nice table, but since it's such a different concept, I thought I spend a few minutes explaining how they work. So the two first steps, if you want to do a surrogate, step 2 is to construct a reduced basis where you take a few waveforms, in this particular case, spanning the mass ratio space from 1 to 10. And using these few waveforms, like picking this reduced basis nicely, allows you to represent all waveforms as a linear combination of the few basis functions. So the one big space saving and time saving is that the reduced basis tends to be quite small. This relies on a data decomposition. So what I'm showing here is only, I illustrate everything with the amplitude of the gravitational waves. And the smarter the data decomposition, so that you have only few features to model, the better the surrogate models will be. Once you have your basis functions, here the 4 in my example, the next step is to do an empirical time interpolation where you identify as many time points as you have reduced basis functions and identify the transformation from data at these time points to the coefficients of the basis function. So that means if you only know the data at your specific time points, you can then interpolate the full time series from that. Moving on, the next step is the hard one, or the hardest one, and that is doing the interpolation across parameter space, where you have your discrete NR simulations and need to come up with fitting formulas that allow you to give the amplitude at any point in between. Once you have this, in order to evaluate now the surrogate, you unfold these steps backward. You have your desired Q that you want, the waveform 4. So from the interpolation in parameters, you can get the data at the time points. And once you have it at the time points, you can go back here, get the coefficients of the empirical time interpolation, and then you can go up here and sum up the reduced basis. Looks a little bit tedious, but it works remarkably well, and you can control and study how well it works with so-called leave K out validation studies. Here what you do is, from the NR simulations that you start out with, you take K away, say K equal 8, and then you construct the surrogate from the N minus K waveforms and use the remaining K waveforms as I check how well it works interpolating the waveforms you haven't used in setting it up. And then you repeat this many times, choosing randomly k waveforms for the validation, and you repeat until you're done. And what comes out of this is essentially the red histogram here that tells you the error of the surrogate that you have been constructing. And in this particular case, the mismatches are around 10 to the minus 4 or so. So it's really, really good. And actually, the mismatches of the surrogate here reach fully the accuracy of the NR simulations, which is this black, bluish dashed histogram here. Here I'm putting down a very recent example from this year for eccentric surrogates. And what you're seeing here is actually the worst matching validation evaluation of the surrogate on top of the NR simulation that it so violently disagrees with. And you can't see a difference because both of them agree within the line thickness.
What's the green, Harald?
The green is a version of a numerical relativity surrogate that uses techniques that are only applicable to quasi-circular methods. And so the point of our paper here was to come out to cook up new decompositions of the data to be surrogated, that it works very well for eccentric systems.
Sorry, so if you use the earlier surrogation method on the eccentric waveform, it is as bad as the green one.
It's as bad as the green. Basically, what happens is that eccentricity introduces a lot more oscillations. And typically, those oscillations are essentially almost randomly occurring in time and across parameter space. And this is very difficult to model afterwards. And so the new thing we introduced, as well as a group here, was to use mean anomaly, the radial phase, as one important parameter in re-expressing the data. Thank you for asking a question, Ajith. Let me use this as an opportunity to ask whether we have any other questions.
The NR errors.
The NR errors are calculated by running the numerical relativity simulations multiple times at multiple resolutions, and then taking differences between different resolutions, so high resolution versus lower resolution.
And this construction is restricted only to the NR part of the waveform.
And the big thing about surrogates is they are restricted. Initially, they are restricted to only where you have numerical relativity simulations. So they are only as long as the numerical relativity simulations, and they only cover that part of parameter space that numerical relativity covers. But you can also surrogate other waveform models, like an EOB model, which naively might be too slow for parameter estimation. You can construct a surrogate of it, which then, if you succeed, will run a lot faster than the EOB model.
Yeah, I was wondering that what is this proportion in which n minus k is taken, because n minus k should be sufficient, and also we have to leave out k also sufficient so that we can validate it back, right? Like in what proportions?
So how big the numbers are is going to depend on what precise model you're constructing. This one here is a model that goes over mass ratio, eccentricity, and mean anomaly. So it's a three-dimensional model only. And that has about 150 numerical relativity simulations behind. And we chose to leave out 8 out for each time we calculate these mismatches. But this 8 is just a validation choice. You can change this around. If you have higher dimensional parameter spaces, you typically need more NR simulations. So for quasi-circular precessing spin simulations, 7-dimensional parameter space, then one needs about 1,000 to 2,000 NR simulations.
I have a very simple, naive questions. So yeah, I'm speaking. So what I see in most of the interpolation is to take care of the dimensions. Here, I think these are interpolated with respect to the intrinsic parameter mass and spin in here, included with the eccentricity. It's quite enough, like large dimension, and also like how do you decide like how to populate the interpolation point as dimension increases? It's going to be lot of interpolation going on in here.
This is a very good question. The way this is done is typically with what's called as greedy placement. So we start out with a large number of randomly placed, easier to calculate waveforms like EOB waveforms, millions of them in the full parameter space. Then you pick one of them, and then you keep on picking more of these waveforms, always the one that has the worst mismatch with all the ones you have already picked. So the first one you might be picking is an equal mass non-spin, and then the worst matching one might be a high spin, high mass ratio one, and then it will jump over the full parameter space and keep on finding waveforms that are as different within the parameter space than what you already have in your training set. And this then leads to sets of hundreds to thousands of target parameters, masses and spins, at which one does then the numerical relativity simulations, which takes many years to do if you want to do thousands of them. And then once you have the numerical relativity data, then you go off and calculate and construct the surrogate model.
Thank you. That answers my question. I was just wondering, in some other high-dimensional interpolation, people use Jacobian and try to see like how fast the points are, like things are changing. Yes.
Sorry, we have a few minutes after the talk as well, so do you mind holding off that question? And
Okay, sure.
thank you.
Okay. A few more examples of waveforms from a few different waveform families, not just my own, also illustrating that aligned spin non-precessing waveforms typically look quite simple, like you might imagine waveforms to look like. Once you put in generic spin and have orbital plane precession, modulations show up. And once you have eccentricity, you get this extra per orbit oscillations that arise from the in-out motion of eccentricity. Okay, numerical relativity is also an important part of this because it's the only one that can cover parameter space and can bridge from in-spiral to merger and ring down. Here's a plot from the Lisa waveform white paper showing the parameter space coverage of the 4 big groups doing waveform catalogs. And the points, what I wanted to highlight here is that as of 23, mass ratio coverage up to 4 was very dense, beyond quite sparse. And spins typically go up to 0.8 or thereabouts, and very rarely beyond. Because high mass ratio and high spin simulations are much more difficult and much more computational costly than low mass ratio and lower spins. With NSXX, my own collaboration, we just put out our new improved catalog, which now has twice as many simulations as before. I think the biggest point to note in terms of parameter space coverage is that we now have quite dense coverage up to mass ratio of 8. There are a few simulations above 0.8. They come in more slowly because they're so difficult to do. So the 0.8 spin limit kind of keeps up. Our new simulations now also have gravitational wave memory. We're deprecating old simulations that we know have deficiencies. And we have a very nice Python package to download and use the waveforms, as well as an interactive web interface where you can find with plots and GUI and mouse clicking at points quite easily which type of simulations might suit your applications the best. Okay, there's more criteria for good NR waveforms when you want to do waveform families, waveform modeling. Of course, parameter space coverage is important, but you also would like to have long waveforms in order to connect into the post-Newtonian regime. You need clean gravitational waves, including clean higher modes, and the NR simulations also need to be accurate. Here's one example. Let's skip this. Moving on more towards the data analysis aspect of things, the LVK analysis use a bewildering range of models in searches to estimate sensitivities and for parameter estimation. The ones up here are the early ones, 01, 02, and towards the bottom is then the current set of waveform models being used. They come with different physics content. These two plots, by the way, are from the catalog methods paper of GWTC4. So no need to write all of this down. The collaboration has done a very good way of doing this. So brief overview, where are we? Binary black holes, quasi-circular. Precessing spins and higher modes are standard, and there's a large number of waveform models. Binary black holes, eccentric. The things we want to have are ultimately precessing spins and higher modes. Currently, one typically has at best one or the other. So there's a lot more to do for eccentric binary black holes to have complete models. It is a full extension of the parameter space of quasi-circular, so no matter. The binary neutron stars, again, at most precession or higher modes. And the black hole neutron star waveform models are in perhaps the worst possible state, a line spin and two waveform models only. The parameter space coverage for the models, you can typically evaluate them at a rather large range of mass ratios and spins, so they will return a waveform. But the higher the mass ratio you are, or the higher the spins you have, the less reliable and the less accurate the waveforms become. So here's one example comparing EOB with phenom. X-axis is mass ratio, up, down is effective spin. I'm sorry for cutting out the label. And yeah, only points shown where the mismatch is at least 0.01, and on the right-hand side, the mismatch is more like 0.3, 0.4. And so you see at mass ratios above 8 or so, mismatches begin to show up. And if you go to high mass ratio and high spins, this is where the models completely disagree with each other, even also for low spins. And this happens to be precisely the region where we don't have NR simulations to guide the model development. For BNS, things are reasonably good, I believe, primarily because their low mass pushes the merger out of today's detector bands, so no worries over there. And also that because of the comparable masses and the low spins, there's only very mild precession effects going on in neutron stars. Black hole neutron star binaries are perhaps the least developed part. There can be strong precession because you have large mass ratios and large black hole spins. The disruption can be in band. There is a big lack of NR simulations. And so what we actually had to do when analyzing the first black hole neutron star binaries with LIGO, we compared aligned spin black hole neutron star waveforms and parameter estimation to aligned spin BBH parameter estimation. And we used to argue this to argue that, in quotes, matter is unimportant. And then we used the precessing BBH waveform models to do the full parameter estimation. I think it worked given the situation we were in, but it's not really a situation we want to be in long term in analyzing gravitational waves. Okay, so I have 6 minutes left to highlight a few of the great things the waveform models did for LIGO, and especially to highlight a lot of the concerning aspects that are still open and will become more concerning in the future. You know, LIGO has observed many events. This is a plot from 2004. And it's typically the edge cases that challenge our models, but they tend to have the largest science payoff. Down here, a NSBH with negative spin. Up here, the most unequal masses. Up here, the highest mass system observed so far. So those are the cases one has to be most worried about and while at the same time being most excited about. Here's a mass ratio 3 case study that just tells that I like to use to illustrate that all the work that goes into waveform models actually matters. Plotted here is inclination and distance. And if you analyze the system with only the quadrupolar gravitational waves, you get the blue contours here, where you can't distinguish which inclination the system is at, and consequently, the distance uncertainty is about a factor of 2. Putting in higher modes and precession cuts down the uncertainty tremendously, fixing a inclination angle and a much better distance estimate. So the physics really helps and pays off in data analysis. On the same time, what I like the signal for is that at the time, the waveform models of the day actually somewhat disagreed with each other in terms of mass ratio and spin recovery. And so this is also an encouragement that the waveform model development needs to continue to reduce systematic biases like the ones here between the two waveform models. The most unequal mass system, 1908-14, again, analyzed with waveforms with different physics content. And I'm plotting here the mass of the small body because one of the important questions is this a neutron star with mass around 2 solar mass or thereabouts, or a black hole with masses of 2.5 or above? It's right at the edge of the maximum neutron star mass, so this is quite a dicey and important question. And with just using 2-2 modes, you get a very broad posterior. And once you put in higher order modes and precession, you get the very tight posterior of 2.6 plus minus 0.1. So again, precession really is important in analyzing signals. And in this particular case, one actually had to have precessing models at mass ratio of 10, which was really challenging at the time. Luckily, the system turned out to have essentially no black holes, no big body spin. So this is the region of parameter space where the models work well and things were fine. The highest signal-to-noise ratio event, immensely small parameter estimation contours, and everything works really, really nicely. But I would like to move on and also skip eccentricity to highlight a few of the shortcomings we currently have in the waveform models. I've already emphasized neutron star black hole binaries. So if you look at this signal here, one of the first neutron star black hole binaries, it has an immensely long tail in the distribution. And up here you have almost comparable masses and large negative black hole spin. This is probably not real, but the waveforms are so uncertain currently that we cannot distinguish and exclude this region of this particular signal. 04 waveform systematics is generally quite benign. These are the 5 worst cases in the 04A analysis. So you see sometimes the masses might be estimated a little bit differently between different models, but nothing really to write home about. Here also a little bit of differences. In this case, there's quite more mass ratio uncertainty. And down here, this is the worst event that we had, also the highest mass event as well, where you see the different models disagree quite tremendously. For this event, I would even call the paper describing it a waveform systematic study with an attached gravitational wave signal. Here's the actual parameter estimation results. The different colors are the different waveform models used in recovery. And you see the masses are quite different, the mass ratios are quite different, the component masses are quite differently recovered, depending which model you have. So definitely an unsatisfactory situation. You can calculate accuracy of waveform models against numerical relativity. You find that for high mass ratio, high spins, all the waveform models lose accuracy except the surrogate, but even the surrogate may not be as good as you wish to have. You can even go on and make NR injections to test how well it works. Quite often it works quite well. This is a numerical relativity injection where all models give consistent answers. But then you also find cases like the one down here, where you inject a precessing numerical relativity simulation at equal mass, and everything recovers a mass ratio of 4. And so precisely what's going on there is still under intense scrutiny. but clearly not a situation we want to be in and that needs to be better understood. What else do we have? The future, we will have much higher SNRs into the thousands, both ground-based detectors and LISA. And we will have source counts of 10 to the 4, 10 to the 5 instead of the current 100. So what this means is we will see much more diverse systems, so the outliers will become more prevalent, more numerous, and the strongest signals will have much higher signal-to-noise ratio. Here's one scary example of what can happen. This is a system, 60 plus 10 solar masses and large spins, quasi-circular. And this is parameter recovery. The masses are never recovered correctly. The distances are never recovered correctly. The sky localization is off. Here's the injected signal. These are the different sky localizations. And this doesn't even work at 05. And with increasing sensitivity of future detectors, all of this is getting worse. So for extreme signals, immense more work in waveform modeling is needed to be confident for the future detectors. And I'll skip the astrophysical effects and postpone them into the plenary session later on and stop here with my summary. Waveform modeling has been remarkably successful so far in underpinning and helping gravitational wave astronomy. It has mostly kept up. Of the 200 events, 195 are analyzed perfectly fine, and it's the last 5 that make trouble. But to continue to extract the most physics or astrophysics or beyond GR information from the most interesting events, we will require immense future improvements. In standard vacuum GR, for systems with matter, beyond GR, and also we need to think about astrophysical imprints as well in order to distinguish them from systematic biases and from beyond GR effects. Thank you very much.
Thanks, Harald, for this nice overview talk. We have time for 1 or 2 questions. Yeah, please.
Okay, thank you for the talk. I wanted to ask that for surrogate modeling of eccentric waveforms, what we do is we take a single eccentricity and we vary the mean anomaly and we construct the SVD. That's how we get the eccentric harmonics. So this is not clear to me that how do we recover eccentric harmonics via this process?
This is a great question, but it's also very technical. So perhaps let's talk about it, the 2 of us, in a break later on.
Okay.
Hi, Harald. Thanks for the very nice talk. My question is somewhat basic. So we know that numerical relativity is the gold standard. So all waveforms are ultimately checked for their accuracy and precision with respect to numerical relativity. So my question then would be, how do you check that the numerical relativity waveforms themselves are accurate? Is there a sort of checklist? Is it that different numerical relativity simulations are compared with each other? So how do you do that?
This is a very good question because you shouldn't believe numerical relativity without questioning it. I'm a numerical relativity expert by heart, and I always cringe when I hear the words gold standard. It's nice to be appreciated, but I also know how complicated it is, how many things go wrong. There's a few important things that are being done. One is each code internally can do convergence tests. So you run the same simulation at different resolutions, and you should find consistent answers with ever smaller disagreements between them. This doesn't catch issues like wrong boundary conditions in the numerical relativity codes, or it wouldn't catch wrong gravitational wave extraction. Then another important part is cross-code validation, that different numerical relativity codes calculate the same system and find the same waveform. This is quite difficult to do. So usually this is done via waveform models that when one constructs a waveform model based on an R of one code, and then one check with an R of a different code. And if there's systematic differences, there's a problem with the NR waveforms. And the third really important part is to cross-check numerical relativity with perturbative results. That at large distances, it agrees with post-Newtonian. That at small mass ratios, it agrees with self-force calculations. So all this, that in the ring down phase, you can recover the quasi-normal modes from perturbation theory from your numerical relativity simulation. So all these tests are done as well. Specifically, I know it very well for SXX and SPEC. We do all these tests and they all pass.
Okay, thanks, Ashwath. Sorry, we are running out of time for this talk. So let's thank Harald again. Time for questions in the